Welcome to our first section of learning about work and energy and conservation. So, the first thing that we need to understand here is, well, what is work? A lot of you guys are thinking, well, this physics class is work, or doing math is work. But when we talk about work in physics, it's the measure of energy. The measure of energy that is transferred. I'm going to write on our dude here. Transferred when a force, we should be familiar with that word, force, acts over a given displacement. So that's really neat and interesting that we're talking about this idea of force and energy being transferred and how that works together and what we're going to do with it. And an important thing to note is that this is a scalar quantity. So keep that in the back of your mind, that this is a scalar quantity, but the relative directions that we're going to use in our formula here are important. And speaking of which, we are going to have a formula. Our new formula is work is equal to the force multiplied by the displacement, so the change in distance. Just thinking about that, let's write this here. The direction is important. For force and the change in displacement. Now, force does not always operate in one direction. As we've known in our last unit that we've done here, is something that we've done a lot of, is we've broken things into component parts and studied what's happening in these things. And you can see in this example over here on the right that we have a force that is being applied down this way. Excuse my bad writing here, which means that we have a force that is parallel and a force that is perpendicular. I'm going to say perp for short. Now, what does that mean? Well, that tells us a few different things. We have a few different cases here. We have our parallel case, we have our normal case, and we're going to have a perpendicular case. So if our normal case is we're just chilling with work is equal to FD. Nothing important is really happening. It's just we're working together and we're trying to figure out what exactly is happening in these things. And sometimes we actually write it more often as the parallel case. So work is equal to the force that is parallel and the displacement. And when I'm talking about the force that is parallel, it is the force, the angle between the direction and the force and the direction of the displacement is theta, and it's parallel to the displacement. So that's why I have this little diagram over here, is that you can see that the direction that is happening here, that the force is happening in an upwards direction, and the displacement is also happening in an upwards direction. Now, if we didn't have this component part, we often write it as well as F cos theta multiplied by the displacement. That also equals work. And that is because that F cos theta, this is parallel to the displacement. This is your X component. And that makes sense if I scroll up and we look at that other example with the guy with the box, is that our parallel one, if I want to find this one, this is our angle, this is our adjacent, that means that this is going to be cos theta. Whereas if I want to find the perpendicular one, it's going to look a little different. And if we're dealing with a force that is perpendicular to the force, so the displacement is happening left to right, but the force is still going up and down. Let's think about this. Our theta is equal to 90 degrees. And if this is 90 degrees, we have cos theta is equal to 0. If you plug in cos 90, 0, there's no work. So when the force is parallel, the work is 0. Or the force is 0, sorry. And I've talked a little bit about energy, but let's get into it. So what is energy? Well, some of you might say your sleep schedule, some of you might say your day-to-day ability to do things, and that's kind of close, is that it's the ability to do work. This is also a scalar quantity. And there's a few different derivatives of this equation and what we're going to do here. The first thing that we're going to look at is we're going to look at gravitational potential energy. And when we're talking about gravitational potential energy, we're talking about something as the way it relates to height. So that is energy due to height. And we have a new formula here. We have EP is equal to mg delta h. And I can't stress enough that this relies on height. So let's remember that we have m is our mass in kilograms, g is our gravitational constant, and delta h, the change in height, in meters. And of course it's not given in one of those, and you just switch it around until you're at where you need to go. I want to talk about this example here. We have figure 6.8, this one, shows a force of 15 newtons while acting on an object that moves over a displacement of 25.0 meters at 25 degrees. What is the work done by this force? Well, we're told that our force is equal to 1.50 or 150 times 10 to the 2 newtons, 0 degrees. And that our change in displacement is 25.0 meters, 25 degrees. We're going to use our work formula. So work is equal to F d. But because when I look at this, let's break this down. We have our F, this is our force. And then what I need is this force that's happening here, this displacement. And then I also have our F perpendicular, so the one that's going to intersect with this guy at 90 degrees. So we can see that when we're finding this, we have, like, this is our component diagram, I should say that. And the component that does work is our F cos 25. So we're going to set this up. It's going to be 1.5. So it's not this one, it's this adjacent one. This guy does the work. 1.5 times 10 to the 2 newtons cos 25 degrees multiplied by 25.0 meters, which is equal to 3.40 times 10 to the 3 joules. That is something I forgot to tell you guys. Our work, where did I put that? That should have been here somewhere. This should have said right here. the unit is in joules. That is how we measure work. So sorry about that. That's the derivative of joules is Newton multiplied by meters. So I'm glad that came up quicker than later. So the work done by this force is 3.4 times 10 to the 3 joules. Okay, our next one here. You pull a sled along a horizontal surface by applying a force of 620 newtons. So we have an object, we are pulling it, and this is actually getting pulled 42 degrees above the horizontal. So I have this little component part here. This broke down to 42 degrees, and this is 620 newtons. How much work is done to pull the sled 160 meters? So I know my change in displacement is equal to 160 meters. So then work is equal to this one right here, this force that's happening, F cos theta multiplied by d is equal to 620 newtons cos 42, 160 meters, to give us a grand total of 7.4 times 10 to the 4 joules. Good, good, good. Now this one references a picture in your textbook. It's just somebody falling in a tower drop. So just a little car, people here. It's a really good example of a tower drop, right? So they have a mass of 500 kilos. What is their change in gravitational potential energy when they are lifted through a height of 48 meters? So we have a change in height. We know our gravitational constant. And we are looking for the EP. So then our formula is EP is equal to mg delta h, which is 500 kilograms multiplied by 9.81 meters per second squared multiplied by our change in height to give us a resounding total of, I'm at 2.35 times 10 to the 5 joules. But then everything should be to 1 sig fig, so this will change to 2 times 10 to the 5 joules. And then we have an example from our textbook. This shows a toy car track set on top of a tabletop. What is the gravitational potential energy of the car relative to the floor? So let's look at this. I know I'm finding my potential energy because it's relative to the floor. It asks for the gravitational potential energy, so our EP. So then I know this is the formula that I'm using. And then I'm looking for the change in height from the top of the track to the floor because it's relative to the floor, so H1. So then our mass of the car multiplied by our gravitational constant multiplied by our change in height, relative to the floor, which gives us an answer of 0.5? 525, I think it is. Yeah, 527 joules. Now, B asks to calculate the change in gravitational potential energy of the car when it arrives at the bottom of this hill here. So we need to find our change in height. And you could plug this all into the formula because our formula deals with having that change of height. So you would just put it like this, delta H. The mass is the same. Kilograms multiplied by 9.81 meters per second squared. And our change in height, which is 0.950 minus 2.1. Run out of a little bit of room there. So then we bring this all back, we plug it in, and this should be a negative because it's dropping in relative from this down. So then we get negative 0.294 joules. So we lose gravitational energy. Lose energy. Okay, and then I want to talk really quickly about kinetic energy. So kinetic energy is the energy due to the motion of an object. So if that sounds confusing to you, let's just remember, like, we've dealt with kinetic energy for a while, and like we've talked a little bit about like our potential energy. Kinetic energy is like when you're pulling back a bowstring and the arrow releases and gains energy, kinetic energy, energy due to motion. Again, we're going to keep with our unit being joules because it's energy, which is also Newton meters. And the formula that we're going to use here is EK, is mv squared divided by 2, where m is our mass and v is our velocity. And then we're going to talk about our example here. On a highway, a car of mass 1.2 times 10 to the 3 kilos is traveling at 20 meters per second, has a kinetic energy equal to a loaded van of 4.8 times 10 to the 3 kilos. What is the speed of the van? So we're given a few different things here. We're given a mass of a car, so mass car. We're given a velocity of the car. And we need to find the speed of the van. So we know that we have the mass of the van. We know we're trying to find the velocity of the van. And we know that the kinetic energy of the car is equal to the kinetic energy of the van. We have everything that we need to know to make our equation work here. We can leave it like this, or we can do two separate solves. It just depends on what you're more comfortable with. So if I do two separate solves, which I am a fan of, I know that the equation is mass velocity squared divided by 2. Then what you do is you say, okay, this mass is 1.2 times 10 to the 3 kilograms multiplied by 20 meters per second squared divided by 2, which gives us 2.4 times 10 to the 5 kilograms times meters squared, second squared, which is another representation of joules. And if that's confusing to you, you just got to remember that newtons is also meters per second squared, and then we said a joule is equal to Newton times meters, so kind of works together. I digress. Now, we're trying to find the kinetic energy, not the kinetic energy, we're trying to find the velocity of the van. We know that the EKV is the same as this one, so let's set up our equation, mv squared divided by 2. I have 2.4 times 10 to the 5 joules is equal to, we know our mass of the van. It is 4.8 times 10 to the 3 kilograms, v squared divided by 2. So then what we're going to do is we're going to multiply by 2. Is equal to 4.8 times 10 to the 3 kilograms, v squared. Then we are going to divide by this. And you could have some intermediate values if you want. Then these guys cross out. So then our big formula now looks like this. The opposite of squaring something is square rooting it. And then when you put all of this into your calculator, (10 meters per second). If you want to write that down too, that if you're trying to find velocity, that it's going to be the EKV multiplied by 2 divided by mass and all square rooted. That is totally an acceptable thing to have, so you don't have to derive that every time. Okay? If you have any questions, please ask, and good luck on your assignment.